Hi, we're moving right into chapter 6, which is going to be about sugars. So, life's sweet molecules. All right. So, we're going to first classify carbohydrates, and then we're going to get into some functional groups. So, if you learned your functional groups already, you're going to be excited about that. And then we're going to talk about stereoisomers, reactions, specifically disaccharides, all right, and polysaccharides. And then we're going to talk about carbs and blood, talk a little bit about disease. So it's going to be a really interesting chapter. First of all, what are carbohydrates? So they are most commonly known as, that's what we call sugars. We talk carbs, sugars, and you need carbs for energy. Your brain needs that to function. Your body needs sugars to function. So you're going to have some different kinds of carbohydrates. Some are going to be complex and some are going to be simple. All right. So you're going to have complex carbohydrates and simple sugars. So complex carbohydrates are going to be your starches and insoluble fibers. Okay. In your starches and insoluble fibers. Simple sugars are going to be really important in your cells. All right. So you're going to need that for your genetic blueprints, DNA and RNA. Right. And so some of the other sugars, I'll give you some examples, are important as markers on the surface of your cells, like on red blood cells. And finally, we're going to talk about specific diseases like diabetes and lactose intolerance in respect to carbohydrate breakdown. Okay, so the simplest of the carbohydrates are going to be your monosaccharides. Mono means one, saccharous, sugar, one sugar. All right, so maybe you have, so like one sugar, right? So you're going to get familiar with this, right? Let's say, oops. Maybe I'll draw down here. So you'll have and let's say this is an oxygen. You have OH, hydroxyl group, hydroxyl, hydroxyl, hydroxyl. All right. So let's say you have one sugar. One sugar is going to be a monosaccharide, right? So the most common carbohydrate, glucose, and here is the formula for glucose, is a monosaccharide. So that's a monosaccharide. That's a good example. They contain, as you can see, carbon, hydrogen, and oxygen. All right. And you'll notice that you have the same number of carbons and oxygens there. So that's a pattern that you're going to see over and over again because monosaccharides have a formula. Like you remember, we talked about formulas before when we were talking about straight chain alkanes and cyclic structures and so on. So the formula that you're going to have here is the number of carbons in is, as you can see, going to be basically the same as the number of oxygens. All right, so that's going to be whenever the N is higher than 3. So, for example, you might have 3 carbons and 6 hydrogens, and you would have 3 oxygens. Okay. And so in some cases, you can have 2 monosaccharides that are going to be joined together. So if you have, for example, right, that's okay, or these are just examples. So you can have 1, 2 monosaccharides that can be joined together. So basically, you're going to have like hydrolysis. So you're going to have these two monosaccharides joined together. All right. And I'm not the best artist on this iPad, but you can have two monosaccharides joined together this way, and then you form what's called a disaccharide. And that can also be split, like example, table salt can be split up back into two monosaccharide units. All right. So this happens through hydrolysis. All right. So that can happen through hydrolysis. So that's a type of reaction that you've learned before. So you have carbohydrates that can come in the form of one sugar, which would be a monosaccharide. So that's one is mono, two is going to be disaccharide. All right. And if you're going to have anywhere between 3 and 9 sugars, you're going to call that oligosaccharides. Oligosaccharides. All right. So that's 3 to 9 sugars. And one of the most common types of oligosaccharides in the body is going to be our ABO, our ABO that helps us to determine our blood sugar. I mean, not our blood sugar, our blood type, like if you're type A, if you're type O, so on and so forth. So that's going to be determined by a sugar on your red blood cells. Okay. So whenever you're going to have more than 10, so we've talked about if there's 1, 2, 3 to 9, if there's 10 sugars, you're going to have a polysaccharide, right? A polysaccharide. So those units can all be connected together by one continuous chain, and it can be branched, right? So it can be straight or it can be branched. All right, so you have a starch, right? So that's an example of a polysaccharide in plants. So it can contain branched chains of glucose that can be broken down, and it needs to be broken down so that it can be producing energy. All right, so starch, that's something that you get from consuming plants, for example. All right, so if you look here, it's just an example of a monosaccharide. You can see here a disaccharide, an oligosaccharide, where you'll have 3 to 9 sugars that are connected together. And whenever we get to these larger numbers, we can have, as you saw, a continuous chain or a branched chain. All right, so polysaccharides can have up to 10,000 sugars in the chain. So quite impressive and can be quite complex and definitely very branched. So the carbs in your diet can be thought of as fibers, which can be broken down into two categories where you have soluble fiber and insoluble fiber. So the fibers that are carbohydrates, and we cannot break that down naturally with the enzymes that we produce. So soluble fibers, those are the kind of fibers that when they mix with water, they're going to form this sort of gel. So you think of soluble fibers, think of like that Kool-Aid that dissolves in water. All right. So really what's happening with soluble fiber is a gel-like substance is formed in the GI tract. And that gel-like substance is what makes you feel really full whenever you consume soluble fiber. And so it slows down the uptake of sugar and cholesterol into your bloodstream. So some of those soluble fiber foods are going to be like oatmeal or lentils, or apples, carrots. Also containing a soluble fiber is fruit pectin. So something that's used to thicken up our product whenever we're making jellies. All right, fruit jellies, like grape jelly, for example. So the fiber in your diet that can be insoluble would not mix with water. But it is important still nonetheless, because it can actually have a laxative effect. So preventing constipation. So one of those types of fibers would be polysaccharide cellulose, all right, like found in some plants. So those types of sources would be grains, seeds, cabbage, vegetable stalks. So just to name a few examples, but I think you get the picture. So these are fibers that have a laxative type of effect. All right, and so let's go through a few of those problems from 6.1. So if we're going to classify the following carbohydrates as a monosaccharide, disaccharide, oligosaccharide, or polysaccharide, let's see. Here we have a seaweed extract containing up to 25,000 carbohydrate units. Let's break this down. So if we have a monosaccharide, we've got one sugar, right? If we've got a disaccharide, we've got 2 sugars. If we got an oligosaccharide, we have how many? 3 to 9 sugars. And if we've got a polysaccharide, we've got more than 10 sugars. Well, I would say 25,000 definitely is upwards of 10. So I would say A is a polysaccharide, right? Okay. B, we have a fiber, a soluble fiber, right? This kind that mix with water, make you feel full, containing 3 to 6 carbohydrate units. 3 to 6, that would be our oligosaccharide. All right. Maltose containing 2 glucose units. Well, that's just going to be a disaccharide, right? A disaccharide. You should be able to picture that pretty well because I drew out something similar. All right, so let's look at 6.3. Identify the following as characteristics of soluble and insoluble fiber. So A, if it can mix with water. If it can mix with water, that would be soluble. B, can lower blood cholesterol. So like one of the examples of soluble fiber is oatmeal. You know, people eat oatmeal as a way of keeping their cholesterol low. So that would be soluble. Has a laxative effect, all right? Like the polysaccharide cellulose that we were talking about, that you'll get from grains and seeds, so on and so forth. That would have a laxative effect. Definitely would be insoluble, right? Insoluble. All right. So let's go back to our PowerPoint and learn more about monosaccharides in regards to those functional groups. All right. So one of the simplest members in a functional family that's a monosaccharide would be known as the alcohols, right? So ethanol is produced by the fermentation of sugars, all right? So ethanol is produced by the fermentation of sugars, and this ethanol that is produced is what we're going to put in liquor, beer, wine, those products that can be consumed, all right? So ethanol can also be an additive in your fuel at the gas station. So you'll notice whenever you go fill up your boat engine, your tank for your boat, you might not want to put ethanol, right? So you'll use the ethanol-free gas. So that way, for sure, a good example to refer to, that ethanol can be used as an additive for fuel. All right. You're probably familiar with that. If you go to the gas station and pump your own gas, that is. All right, so functional groups and monosaccharides. All right, still looking at alcohols. So primarily in this section, we're going to look at alcohol. So you're going to get really cozy with those alcohols. As far as the literature goes, they are going to be classified specifically by the number of alkyl groups. Okay, so what am I talking about? I'm talking about the carbon. So this is referring to a carbon as attached to a hydroxyl group. All right, so your hydroxyl group, that's that OH, right? That is what is going to constitute or determine whether something is an alcohol, right? And you remember that because you studied your functional groups. All right, so whenever we're going to have one alkyl group, if you look here, if you have one alkyl group attached to the carbon that's attached to an alcohol, that's going to be known as a primary alcohol. So if you find your hydroxyl group, look to see which carbon is attached to the hydroxyl group, and then you can say, you can look for how many carbons are attached to that carbon. And if there's only one, that's going to be a primary alcohol. All right. And furthermore, for a secondary alcohol, if you have a carbon, all right, that is bound to your hydroxyl group, all right, so you know you have an alcohol, then you look to see how many carbon groups, how many carbon groups are bound to this carbon. And you see that there are 1, 2 groups. This is a secondary alcohol. And furthermore, if you have your hydroxyl group, you're going to look to see what carbon it's bound to. And then you're going to count how many carbons are bound to that central carbon. And in this case, if you have 3, you have a tertiary alcohol. It's alcohol because you have a hydroxyl group. All right, a hydroxyl group, and that's your OH. All right, you guys are familiar with this by now. Okay, so we need to classify each of the following alcohols as primary, secondary, or tertiary. So the first thing we're going to do is find the alcohol. All right, then we're going to find the attached carbon, and then we're going to look to see what other carbons that central carbon is attached to. And so we see that we have essentially these 2 CH3s right here. So this is definitely going to be a secondary alcohol. All right. And here you see that you have your alcohol group attached to this carbon, which you know is attached to 2 hydrogens, but we're not worried about that. You know it's attached to 1 carbon right here. And so that is going to be a primary alcohol. All right. So this is isopropyl alcohol that you use sometimes as an antiseptic, right? Rubbing alcohol. So there are other functional groups to keep in mind besides just alcohols. So we're going to move into talking about aldehydes and ketones. All right. So the aldehyde family are going to have carbonyl groups, right, with a hydrogen atom bonded to one side. of the carbonyl and an alkyl or aromatic group bonded to the other side. So monosaccharides can contain an aldehyde functional group at one end. So these are, so like you'll see right here, you can have definitely an aldehyde. So where you have this benzene as your R group, right? Because if we're going to have an aldehyde, we are going to bind an R group, and in that case, it can be a benzene. All right, so this would be something very aromatic. It has a certain aroma to it, and we would name this for both of those components. So that's benzaldehyde. All right, and also another example is formaldehyde. All right, so in this case, you have your aldehyde, all right, and you have a hydrogen bond on this side. So formaldehyde, that is a carcinogen. So we used to use that as a preservative for materials that we would later dissect. But actually that's not used anymore. But something that is very similar that has an aldehyde is but is not so dangerous, is actually used as the preservative, and it has actually a similar aroma to formaldehyde. So that's what you're smelling whenever you're dissecting things, usually these days. All right, so we talked about aldehydes. You can also have ketones. All right, so whenever you're going to have a ketone in a monosaccharide, just remember that they are structurally similar to aldehydes. Remember how they are similar, right? And don't forget how they are different. So ketones, all right, they're going to have an alkyl or an aromatic group on both sides of the carbonyl. So they're going to have both sides has some sort of alkyl or aromatic group. So you can remember that as, so ketone, all right, so these are going to both be R groups. So if you need a key, then you must also have a lock. That's two things. So you can remember that way. So for ketones, you have to have two R groups. All right, so that's the difference. So you're thinking carbonyls in similarity with aldehydes, but also you have to understand how they are different, right? And so they are present in biologically relevant compounds. All right. So whenever we are going to be naming these monosaccharides, you're going to have to, once again, to be able to apply this, understand the rules or the steps that you must use. All right. So if a sugar is going to contain an aldehyde functional group, all right, an aldehyde, you're going to say that that is an aldose. Ald for aldehyde, and so ald for aldehyde, and ose for sugar. All right, so ose, like glucose. You've heard that before, that's a sugar. So, and one that contains a ketone with a functional group is ketose. So ketone, ose is for sugar. Ket for ketone and ose for sugar. So whenever a monosaccharide is going to have 3 carbons, so you're going to be counting again, you're going to use those Greek prefixes. So you will say triose, or if you have 4 carbons, tetrose, 5, pentose, so on and so forth. All right, so if you have this example, all right, so you're going to count your carbons where you have 1, 2, 3, 4, 5, 6 carbons in this chain, and you have an aldehyde. All right, so you're going to have to say aldo, and you have 6, and it's a sugar. So, all right, you have aldohexose. And if you have 1, 2, 3, 4, 5 carbons in this chain, and it has a ketone functional group, that's a ketone, right? You've got 2 R groups, all right? Definitely true. So you have a ketopentose. Ketopentose. All right, keto for ketone, pent for 5 carbons, ose for the sugar. All right, so pretty straightforward, I think. Okay, so you are going to, let's see, I think we're going to go over those problems in class. Let's go over to your problem set. All right, so let's take a look and classify these alcohols as primary, secondary, or tertiary alcohols. All right, so A. So let's see. Let's first find our alcohol. All right, and it's right here. Now we're going to find the carbon that's attached to the alcohol. All right, so right here, and we're going to look at the carbons that surround that alcohol. All right, we're not going to worry about hydrogen. So if we have 1, 2, all right, so we have 2 carbons that are bound to this carbon that's attached to the alcohol group. That is going to be a secondary alcohol. All right, B. So you can write this out also if you need to. So how many carbons are attached to this alcohol? So if you write this out, you will see that this is a primary alcohol. All right, so that is going to be so and so forth. This is the carbon that is attached to the hydroxyl group is attached to 1 carbon. So that is a primary alcohol. All right, so let's look at this next example that's drawn out a little bit. So let's find our alcohol, the carbon that it's attached to, and let's see how many carbons are attached to that carbon. All right, so there's going to be this one, and this one, right? So that is going to be a tertiary alcohol. All right, so let's see here. D, we have our hydroxyl group. We have our carbon that's bound to our hydroxyl group. And then we have our carbons that are bound to that carbon. And that is going to be a what? 1, 2. Secondary alcohol. All right. And let's do that one in class. 6.7. Okay, so let's see. Wants to identify each of the following compounds as containing an aldehyde or a ketone. All right, so remember what's the same, carbonyl, and what's different? The R groups, right? The ketone is going to have the 2 R groups. All right. So, all right. So first, what do we have? So we have our double bond to carbon, all right, which is going to then be bound carbon, carbon. So this is definitely what? That is going to be a ketone, right? And now we have our oxygen double bound to carbon, which is bound to this carbon and this carbon. So these are both going to be R, all right? So neither one is just H, right? So this is a ketone, all right? So here you have your oxygen bound to carbon that's bound to this structure, all right? So this R, rest, and hydrogen. So that is going to be an aldehyde. All right, that one's going to be just aldehyde. Let's see. Okay, we are going to classify the following monosaccharides by the type of carbonyl group and the number of carbons. All right, so let's do this. So what are we going to do? First, we're going to need the functional group. So that's either going to be aldehyde or ketone. So aldo or keto. 2, we need the number of carbons. And 3, what else do we need? Ose, because that's sugar, right? Sugar. Okay. So how many carbons do we have? All right. So 1, 2, 3, 4, 5, 6. We have 6 carbons, and we see that our group is what? We have a hydrogen here. So, and then we have this R group. This is an aldehyde, so it's aldo. And then we have 6 carbons, so that's hex, then ose for sugar. All right, let's do B. So your functional group is what? There's an R. Here's another R. That's a ketone, right? So that's going to be keto. And you have 1, 2, 3, 4, 5. 5 carbons, so that's pent. It's sugar. Ose. Pentose. All right. All right. So, C, we are going to have, let's see, this is an aldehyde, right? So we're going to say aldo, and we have 1, 2, 3, 4 carbons, so tetrose. All right, and I think that's it. So let's look at the slides for 6.3. I know this is going to be a long video. You can break it up if you need to when watching it. All right, so here we're once again talking about our monosaccharides, but in 3-dimensional structure. All right, so like tetrahedral geometry. So remember chiral centers where we had a center carbon that was attached to 4 different groups. All right, so we're going to be thinking about those again. So whenever we're going to have a compound, and this is a reminder, with a single chiral center, all right, they can exist as enantiomers. All right, so do you remember what enantiomers was? All right, so are we talking about superimposable or non-superimposable? What are enantiomers? So I'm going to draw out an example. All right, let's say you have this molecule. And you have this one. Now, if I took this molecule and tried to put it directly on top of this molecule, would they be totally superimposable? No, they wouldn't. They're mirror images instead, right? And so this is what enantiomers are. These would directly overlap the hydroxyl groups, right? And ethyl, but these would not overlap, all right? Your hydrogens would not overlap, and this methyl would not overlap, all right? So these are going to be enantiomers. So your body can recognize molecules that are arranged differently in the 3rd dimension. And that's how specific your receptors are. So enantiomers and the concept of understanding enantiomers is very important biologically. All right, so how many chiral centers does a glucose molecule contain? All right, So let's take a look at this. So the carbon 1, you remember the rules for chirality. If you're going to have double bonds and triple bonds and multiple bonds to hydrogen, you're not going to have a chiral center. So this first carbon is not chiral. The next carbon, if you look, it's attached to this different carbon. All right, so let me erase some of this. All right, and you're going to be bound to a hydrogen and a carbon. So this is a chiral center. And because you have this hydroxyl group down here, all right, you have this group up here, which is also different. All of these other carbons are going to be chiral if you take a look at them. All right, they're all going to be different from each other, and they're all going to be tetrahedral. All right, except for the 6 carbon, because it's bound to 2 hydrogens, right? All of these other carbons in the middle are going to be chiral, right? So we can say that glucose has 4 chiral centers. All right, glucose has 4 chiral centers. All right, so this is basically sort of just what we were going over. So the more stereoisomers you have, is going to be a factor of how many chiral centers are present in a molecule. All right, so the more chiral centers, the more stereoisomers there are that are possible. So if you only have 1 chiral center, you're only going to have at most 2 stereoisomers. Okay, so the general formula is that the number of stereoisomers is going to be 2 to the power of n, where n is going to be the number of chiral centers. So for example, glucose, you remember, had 4 chiral centers. So that means 2 times 2 times 2 times 2, 16 stereoisomers. So we're going to play around with glucose a little bit as our model to understand stereoisomers for monosaccharides. All right. So, all right. So we are going to have 1 stereoisomer of glucose. That's what our body really wants. All right, and that's going to be the D-glucose. So a certain configuration of glucose. And so the 3-dimensionality of these sugars can be better illustrated with a different type of drawing that we haven't done before. That's called a Fisher projection. All right, so before we were using dashes and wedges to indicate dimensionality, and instead now we are going to be using horizontal lines to represent chiral centers. So wherever you're going to have wedges, where something was coming out at you, this is going to be a horizontal line. And where you had dashes where it was going into the background, this is going to be a vertical line. So you have this ball and stick model here. So you can see these are your carbons, all right? And so you have this carbon that you can see is going into the background, and this carbon that's going into the background. And before we looked at this as represented by wedges, but now you can see this is a vertical line, all right? And so here you have this horizontal line, and these are our, here are our elements that are coming, out towards us. So here we have this hydrogen, and here we have this, our compound, our hydroxyl group, all right, coming out towards us, and this is represented with a horizontal line. So these are going to be our Fisher projections. All right. And so this just basically explains what I was telling you. So the chiral carbon is not going to be shown as a C. It's just going to be implied as an intersection of those lines. So it's a more efficient way of understanding where chiral centers are. So wherever you're going to see the lines intersect, those are going to be chiral centers. All right. So the designation of D or L is going to be based on a Fisher projection. And as I said, your body can understand very specifically whether something is D or L oriented, and you're wondering what that means. And I'm going to show you in the next few slides. All right. So let's look at glyceraldehyde. And I see that there's a delay whenever I'm switching slides. Before, where we had glyceraldehyde with the wedge and dash, where you have L-glyceraldehyde, you can see where you had parts of the molecule that were going into the background and parts that were coming out at you. But whenever you're looking at the Fisher projection, now you're just going to have these vertical and horizontal lines, very neat and organized and easy to look at. And so you see that this is where you have your chiral carbon. All right. And so the way we're going to understand if this is L or D configuration is going to be based on a few things. So first, you're going to have to follow these steps to be able to understand whether something is L or D. So if we look at the L configuration of glyceraldehyde, what we do is we look at, so we find our functional group, all right, and we find the carbon that is farthest from that group, and we look to see if the hydroxyl group is on the left or on the right. And in this case, the hydroxyl group is on the left. So like left, L, left, that's going to be the L configuration of glyceraldehyde. All right. And here you're going to look for that carbon that is farthest away from the carbon in our functional group. And that is going to be our hydroxyl on the right in this case. And that is D-glyceraldehyde, D-glyceraldehyde. All right. And so this just sort of gives you an illustration of how L and D-glyceraldehyde are related to each other as mirror images. All right. And here, once again, reinforcing to you how the chiral center looks on these Fisher projections. Okay, so D sugars are going to have the hydroxyl group. The hydroxyl on the right side of the carbon farthest from the carbonyl. All right. Let's see. Let's see, how exactly are we supposed to fill in these blanks here? I'm not sure why they're not filled out on these PowerPoints, because it's supposed to be. These sugars have the, let's see. Just basically, they're going to have the hydroxyl group that's going to be on the chiral carbon farthest away from the carbonyl group on the right side of the molecule. And that's going to be opposite of that for the L enantiomers. All right, remember enantiomers, that's the mirror image, right? So that's going to be the left side of the molecule. So the ones that our body really likes are going to be the D sugars. All right, so D glucose. All right, our body will eat that up all day. We need that to function. We need that to think, to walk around, breathe, just about everything. So if you are looking at the wedge dash projection of the D glucose, right, it's going to look like this. And if you're going to draw it out as a Fisher projection, it's going to look this way. All right. So it's a little bit, you can see how this is a way of identifying those chiral carbons a little more easily. All right, so when drawing enantiomers, using Fisher projections, you're going to write them as if they are mirror images, all right? So the atoms that are going to be on the right side of one enantiomer, all right, are going to be on the left side of the other. For example, so we have D-glucose and L-glucose. If we leave this all the same, all right, we're just going to leave this the same. We are going to move everything on the left side to the right side, and we are going to move everything on the right side of this molecule to the left side. So you can see everything has been swapped. All of those groups on those chiral carbons have been swapped. This is true for an enantiomer, okay? That's true for an enantiomer, right? And what do we like? We like D-glucose, all right? We can break that down. That's what we need, our fuel. So whenever you're going to draw an enantiomer, all right, you are going to locate the chiral centers first, all right? And then you're going to swap the horizontal groups. Okay, so just as I did before, you're going to take what's on the left and put it on the right side of those chiral carbons, and you're going to move those groups that are on the right, and you're going to put them on the left. All right, so it's just as simple as that. And we're going to leave this alone. We're only changing the groups on those chiral carbons, just as I showed you here, okay? So that's how you're going to draw enantiomers. It's pretty straightforward. All right, so if we're going to draw the Fisher projection for the enantiomer of D-ribose, ribose, all right, that's a really important sugar, right? Ribose. I think you've heard of it before, and we'll talk about it a little bit. But all right, so we're drawing this out. All right. So we've got 1, 2, 3 chiral carbons. All right. So on one side, we're going to have our hydroxyl groups. If hydroxyl is going to be on the left, that's going to be L-ribose. All right. And it's really just as simple as that. All right. So we talked about glucose having stereoisomers, around 16 different ones. But you have 4 chiral carbons. You're wondering, how can there be that many enantiomers? Well, in some cases, you're going to have diastereomers, all right? Diastereomers. So those are stereomers that are not exactly mirror images, all right? And so in these cases, you might not have every chiral carbon that is going to be, I'm sorry about the lag on the slides, that is going to be swapped from left to right. So you can see here with D-glucose and D-galactose. So these are going to be diastereomers, right? On this first chiral carbon, we do not have a swap, right? They are not flipped. Is it flipped for our third carbon? Nope. Is it flipped for our fourth carbon? Yes. And it's not flipped for the fifth carbon, right? So because we have this one case, all right, they are not mirror images, but they are going to be diastereomers, all right? And so here is a table of monosaccharides that basically are going to be having 3 to 5 of those. All right. And so you can go ahead and look at these and see how many varieties there actually are. And just to understand how you can have so many different types of isomers. All right. So let's talk about some important monosaccharides. So the first one that we're going to talk about is glucose. So that's going to be the most prevalent sugar that's going to be in nature. All right. So, and also dextrose, so blood sugar. So we're going to talk a little bit about the regulation of glucose. So this is a really, really important monosaccharide, and you've probably heard it before. It's pretty ubiquitous. It's found in fruits and veggies, corn syrup. It's found in a lot of places, a lot of things that you consume. So it can be broken down inside of your cells in a process called glycolysis. So you need to use glucose and you break it down with glycolysis. So people that have the disease diabetes, they can under their cells are perfectly capable of glycolysis, but they have problems with getting glucose from their bloodstream into the cells so that glycolysis can occur. So you have to constantly monitor the amount of glucose that's in the blood. All right. So you can end up having a high blood sugar, high blood glucose whenever you have that disease. So, all right, let's move on to another monosaccharide, and that is galactose. So that is a sugar that is found in milk, all right, dairy products, galactose. It has a single chiral center, all right, on its 4th carbon, and it's oppositely arranged to glucose. So if you think of what type of isomers there could be, so diastereomers that differ by just one chiral center, only one chiral center, are going to have a special name, and they are epimers. All right. So your body can use galactose. If you don't have glucose, it can use galactose and can convert galactose to glucose. All right. So if you don't have glucose, but you have galactose, you're okay, because you can convert galactose to glucose, which you need using an enzyme called epiramase. All right. So it can change from one epimer to the other. You can go from galactose to glucose. All right. As long as you produce this enzyme, then you're good. All right. Galactose. So another important sugar is going to be mannose. So mannose is commonly found in cranberries. All right. So that's something really notable about cranberries, is that they have the sugar mannose. Okay, so you ever heard of drinking your cranberry juice whenever you have a UTI? All right. So there are a lot of studies that are in place understanding the role of mannose in these infections and how drinking cranberry juice can be a positive. Sorry about pausing it. I keep having a lot of knocks on my door. All right. So you know that cranberry juice is promoted for treating UTIs, and it's related to excess mannose being flushed through your UTI. So that's helpful with urinary tract infections. And there's a lot of studies that are being done to understand whether the role of mannose in these infections is positive or negative, and what is actually protective. Okay. So another important monosaccharide is fructose. All right, so we also call that our fruit sugar. All right, so it's the sweetest of the sugars. And it's found in fruits, vegetables, and honey. All right, so those are some of my favorite sugars. All right, so it likes to combine with glucose. All right, so it gives us our disaccharide, sucrose in that case, and it is 1.5 times exactly as sweet as table sugar. So the receptors on your tongue and in your mouth for taste are that specific to the structure of that saccharide, that's what determines how sweet that fructose is relative to the other sugars, for example. So even though, so it's not just an epimer of glucose, it's not an epimer of glucose, it can be broken down also and utilized for energy production. All right. So again, I told you we would talk about ribose. Where have you heard of ribose before? Deoxyribonucleic acid, right? So these are pentoses. So pent, 5 carbon sugars, all right? And 2 deoxyribose. They're both going to be nucleic acids, part of nucleic acids that make up our DNA. So they make up the blueprints of your genetics. And there are 2 types of nucleic acids that are distinguishable by those types of sugars. All right. So when you have RNA, all right, you're going to have ribose, and DNA is going to specifically have deoxyribose. All right. So those are really different. So the difference between those sugars is that whenever you look at the 2 pentoses, all right, an oxygen atom on the second carbon is going to be absent for deoxyribose. All right, so you see that you have that oxygen on the second carbon for ribose. On the second carbon for deoxyribose, you don't have that oxygen. All right, so that's where you're going to have that difference. And ribose is also going to be found in the vitamin riboflavin and a whole bunch of other important molecules that your body needs to use. All right. So glucose and diabetes. All right. So this is really important. I think this is really the kind of stuff that is very important for you to know. So your glucose levels in your body are regulated specifically by 2 hormones, insulin and glucagon. All right. So after you eat a meal, all right, your body is going to say, so you're going to eat a meal and the blood sugar is in your body is going to go up, and your body is going to say, make insulin, make insulin. All right. And that insulin is going to help to take up some of that glucose out of your blood. All right, out of your blood. So whenever you're going to have these peaks, all right, you're going to be producing insulin right after you've eaten a meal and you have this peak of glucose in your blood. All right, let's say this is glucose. Then whenever you get hungry, all right, that's going to go down. All right, so glucose gets low. All right, so you're not making insulin so much, and then it's going to peak again, and then you're going to get hungry again. It's going to peak again. So whenever you peak like this, whenever you have these peaks, you're going to make insulin. All right, and whenever you have periods of fasting, like whenever you go to sleep and you're not eating, right, you're going to have dips in glucose. And whenever that happens, your body is going to produce something called glucagon. And so whenever you have these dips, your body is going to produce glucagon. All right. And glucagon is going to tell the liver, hey, you need to, put out some of that glucose into the bloodstream. So it's where you're going to have some of that stored glucose, right? In the liver, glucagon is going to say, hey, we need to break this down. We need to break down all of this stored energy into glucose and put it into the bloodstream so we can function. All right. So you're going to have insulin and glucagon. All right. That's going to tightly regulate the blood sugar in your body. And people that don't regulate this process so well have diabetes. So that's whenever, for prolonged periods of time, somebody has high blood sugar. All right. They have too much sugar in their blood. I almost said too much blood in their sugar. Too tired. All right. So, in this case, all right, you can have two different kinds of diabetes, right? You can have one type of diabetes where you don't produce enough insulin. You just genetically, you just don't produce enough insulin. There's a lot of studies on diabetes type 1 and the causes of that. And so whenever you have this, you need to have supplemental insulin, all right, to supplant that insulin that you don't have so that you can take some of that excess glucose out of the blood. And type 2 diabetes is different. It's where you can make insulin just fine, just the insulin signal is not received by the cells. And a lot of times, instead, this can be treated with diet and exercise, weight loss, and medication. All right. Basically, I think this is a really important concept for you to understand. All right. And I believe that we are going to work some problems in class. Or are we going to work some problems right now? Are we going to work some problems in class? See, let's work some problems in class. All right. And I might make another video with problems. Thank y'all. I know it's long. Thanks.